Welcome to Học Tiếng Anh với Joseph, where we build vocabulary and practice pronunciation through reading. Continuing with The Cat in the Box, a history of science in 100 experiments. Today we read story number 53, Sparking Radio into Life. Electromagnetism, Maxwell's equations, and light were all cornerstones of scientific experiment and research in the late 19th century. At the same time that Michelson and Morley were carrying out their experiments, in what proved a futile attempt to find evidence for the ether, the German physicist Heinrich Hertz was making a breakthrough that not only provided further proof of the accuracy of Maxwell's theory, but also opened the way to modern communications. When Maxwell found that the equations that describe electromagnetic waves determined that these waves must travel at the speed of light, he not only concluded that light must be a form of electromagnetic wave, but predicted that other radiations could be propagated through the electromagnetic field according to electromagnetic laws. It was these other radiations, now called radio waves, that Hertz rediscovered in the mid-1880s. Following the footsteps of Michael Faraday, Hertz had been carrying out experiments involving induction using a pair of Rice spirals, coils of wire wound like a solenoid, with their ends connected to metal balls separated by a small gap. He noticed that when electricity from storage device known as a Leyden jar was discharged into one of these coils, a spark jumped across the gap in the other coil, even though the two spirals were not physically connected and were not, as in Faraday's coils, wrapped around a shared iron rod. Some influence had traveled through the space between the spirals to make the second one spark in response to the activity of the first one. In order to investigate the phenomenon, Hertz scaled up his experiment. He used an electric generator and an induction coil to make sparks, not in the right spiral, but across a gap in the middle of a piece of wire 6.5 feet or 2 meters long, ending in spheres 4 mm in diameter. The long wire acted as a radiator for electromagnetic energy. The electric current associated with the sparks bounced to and fro along the wires. Various pieces of equipment were used to detect the waves being radiated by the antenna, the simplest being a piece of copper wire 1 mm thick, bent into an almost complete circle 3 inches or 7.5 centimeters across. There was a small brass sphere on one end of the wire. The other end was pointed, nearly touching the sphere. The adjustable gap between the point and the sphere was typically a few hundredths of a millimeter. Sparks leaping across the gap in the transmitter produce corresponding sparks in the receiver, and by moving the receiver to different distances from the transmitter over a range of a few meters and measuring the strength of the response, Hertz could measure properties of the waves being radiated. He also carried out experiments in which a zinc plate was used as a reflector to generate standing waves for study. In a series of experiments carried out between 1886 and 1889, Hertz found that the waves were 13 feet or 4 meters long, twice the length of the transmitting antenna, and traveled at the speed of light. He showed that these waves, they could be reflected and refracted like light and focused by concave reflectors. This was a dramatic confirmation of Maxwell's theory of electromagnetism, since visible light has wavelengths in the range of 400 nanometers to 700 nanometers. A nanometer is a billionth of a meter. A Hertzian waves were roughly 10 million times bigger than light waves, but obeyed the same rules. All of the discoveries were published in a series of papers in the journal Annales de Physique before being presented in Hertz's book, Investigations on the Propagation of Electrical Energy in 1892. The book is now considered a classic, but Hertz had no idea of the practical implications of his discovery. He told a student, "It's of no use whatsoever. This is just an experiment that proves Maestro Maxwell was right. We just have these mysterious electromagnetic waves that we cannot see with our naked eye, but there they are." "What's next?" asked the student. Hertz replied, "Nothing, I guess." He was wrong. The waves he discovered, now called radio waves, revolutionized communications in the 20th century, laying the foundations of radio, radar, TV, and the wireless society on which we now depend. Appropriately, the modern unit of frequency cycles per second is named the Hertz in his honor. In those units, the waves investigated by Hertz had a frequency of a few hundred megahertz, generated by a half-wave dipole antenna. Let's move on to the vocabulary section. Electromagnetism. Cornerstones. Evidence. Accuracy. Modern communication. Propagate. Induction. Right spirals. Wound. Electric generator. Diameter. Antenna. Transmitter. Leaping across the gap. Concave reflector. Nanometer. A billionth of a meter. Thank you for your time, and as usual, I will see you in the next story. Bye for now.